Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everybody, today it's my pleasure to introduce Alp Kupku from Brown University. Alp is a grad student at Brown University who works with Anna Lisanska. It's actually been my pleasure to work with him for the past couple of years, so he's a great guy. And now I guess he's going to be telling us about the great work that the Brownie Points project has been doing at Brown for the past couple of years.
Thanks, Mira. So, I'm Alp Kupku, as Mira said, and I'll be talking about incentivizing outsourced computation. I just gave this talk at the NetEcon conference, and hopefully it will be good it will be fun for you too. This is joint work with Mira and Melissa here, and also Chris Irwin, John Janati, and Anna Lisanska from Brown University. We planned to outsource this talk even to Kevin, but then eventually we decided that I should give the talk. So, in our outsourcing scenario, we have Marge who wants to vacuum clean the house. And as we all know, it's a really computationally intensive task. So, she can't do it alone. She needs to employ some family members. Like, she needs to outsource this task. So, Marge is our boss who is trusted. Vacuum cleaning the house is the job, which is an algorithm plus an input. And Simpsons are contractors, but they are untrusted. They can be honest, lazy, malicious, like all kinds of contractors. So we need to work with such untrusted contractors. And our goal is to reduce the boss's load while getting accurate results. So in our model, the assumption is that boss can reward contractors if they perform the job correctly, or if they perform the job incorrectly, boss can fine them. And contractors will not be employed unless they can pay this fine. So, boss have also some other capabilities. You can employ multiple contractors or double check their answers. So, what are some sample outsourcing scenarios currently that are available? The two famous ones are SETI at Home and Rosetta at Home projects, where the job is to search for aliens or some protein structure, and the boss is the Berkeley Boeing server. So they reward and fine contractors using some reputation points. And as Mira said, we have the Brownie Points project at Brown University. The idea there is to use electronic cash for peer-to-peer file sharing to provide accountability and fairness. So the job there is to verify those e-coins that are used in the system. And of course, the boss is the bank. And the contractors are other users in the system who are rewarded or fined through those e-coins themselves. So this makes the e-coins, the rewards actually fungible because they can be used in this file sharing scenario to buy the files. But regardless of the reward being fungible or not, we are assuming that the contractors value these rewards. They want to earn the reward. So let's begin with analyzing some related work. There are those Spawn, Popcorn, and Tycoon systems which allocate grid computing resources using some auction-based mechanisms. And they assume a friendly environment. They are not trying to incentivize people. They are not dealing with malicious users at all. There's this Boeing and distributed.NET projects I just talked, SETI at Home and Rosetta at Home, which are based on this reputation economy. And Molnar, in 2000, in one of his articles, informally proposes one of the solutions we will use, a hashing solution. But we have a formal definition of the solution, and we also analyze how to incentivize rational contractors with those and how to deal with maliciousness. In terms of maliciousness, there's the Byzantine fault tolerance and the bar model. The bar model corresponds to Byzantine, so malicious users, altruistic, so honest users, and rational users. This model corresponds to our case, but in those works, they typically assume a quorum of users being honest, typically 2/3 of the users. So what are the problems we'll address? First of all, why would a contractor do the job at all? As I just said, to gain the reward, whether it being e-coins or some reputation points. But then why perform the job correctly? The idea is that if the incentives are set correctly, they will be getting more rewards. And we will show a solution that uses hashing to force this correct behavior. And also, to reduce boss's load, we will show how the boss can employ multiple contractors for the same job. And then finally, we'll deal with the question of how to protect the boss from these malicious users. And we will show that the accuracy loss and the resource waste caused by such malicious contractors are limited. We will provide bounds for that when we use appropriate fine to reward ratios. So let's begin with the question of why do the job at all. Remember, there's a reward and a fine. And let's define cost of doing the job with perfect accuracy as cost 1. So then the utility of an honest contractor becomes this reward minus this cost, of course. And as long as this is greater than 0, there will be an incentive to participate in the system. But why perform this job correctly? Why not just guess, right? For example, for SETI at home project, just guess that there's no alien life. And for the brownie points project, just guess that the ecoin is valid. Those guesses will be highly correct, I mean, most of the time. So in general, why not just use an alternative algorithm, which is correct with some probability Q less than 1, and it has a lower cost. So just be lazy, why not? Oops, sorry. Why not? So let's define the lazy contractors, like Homer here, to be the ones that use an alternative algorithm. He will use the broom instead of the vacuum. So of course he will be caught with some probability P when he uses the broom instead of the vacuum. And this probability obviously depends on him being incorrect, which is this 1 minus Q, where Q was the probability of being correct. And some probability of getting caught when he returns an incorrect answer. And let's define this as P catch and not worry about it for now. Just for now. So then the utility of Homer as a lazy contractor becomes he gets the reward when he is not caught, he gets fined when he is caught, and of course he pays some cost. And remember, when this Q was 1, so the job is performed with perfect accuracy, this converges to a utility of an honest contractor. So under these circumstances, how can we guarantee some minimum accuracy Q? So we want some minimum accuracy, the capital Q, and we cannot assume anything about the cost of any alternative algorithm such a lazy contractor can use. But we still want the utility to be less than or equal to 0 for all accuracies that's less than the minimum accuracy we want. So we show that if the boss sets the fine to reward ratio to 1 minus P over P, where this P, the probability of getting caught, is computed with this P catch times 1 minus this minimum accuracy we want, then all the rational contractors will be incentivized to perform this job with this minimum accuracy. So, but there are some problems with it. If you want a really high minimum accuracy, we need a really high probability of catching them, or we need really high fine to reward ratios. And fine to reward ratios, if they are high, it's problematic because remember, the contractors will not be employed unless they can pay the fine. So just to give an example, if you want a minimum accuracy of 99%, and if we just double check, let's say 1 out of every 1,000 jobs, then the fine to reward ratio has to be at least 100,000, which seems unreasonable. So ideally, we want everyone to use this vacuum instead of the broom, and we want to achieve this with low fine to reward ratios. So how can we do that? Just consider a simple multiplication operation. To be able to reach this result, you need to perform some intermediate steps. So we will require the hash of these intermediate steps together with the result. So when a contractor returns a result, he has to return this hash of these intermediate steps together with it. The idea is that if the contractor uses some other algorithm than the one directed by the boss, then it will be impossible to return the correct hash. Almost impossible, of course. But so for example, the intermediate steps for a broom and a vacuum will be different. And then we show that if the boss sets this find to reward ratio to 1 over this probability of catching, then every rational contractor will be using the vacuum, not the broom. And we don't have to worry about the accuracy anymore. This will provide us almost perfect accuracy. So I was talking about this probability of catching the incorrect answer, but how do we do that? One technique might be just employing one contractor per job and randomly double checking the answer with some probability, let's say p-check. Then of course the probability that we catch an incorrect answer is the same probability that we check that answer. And less checking will mean less work for the boss, but the problem is it will require high find to reward ratios. Remember, it was inversely proportional. And if we want to catch them more often, we need to do more checks. So it's a waste of resources. So what can we do? I just said we can use multiple contractors as another technique to reduce the boss's load and achieve a high probability of catching. So how do we do that? The idea is that Marge will outsource the same job to m random contractors and double check their result if the contractors return different results. Why do we do that? We don't take the majority of the results and so on because we don't want to assume an honest majority as in the case of the Byzantine fault tolerance model. This will be clear when we deal with malicious users actually. So in the multiple contractor scenario, the assumption is that we have a worst case assumption. All the lazy contractors will be using the same algorithm. So they will return the same answer, which means when they return the same incorrect answer, boss will not be catching them because boss will not double check. So the rules of the game is that the utility of an honest contractor is just as before, the reward minus this cost. And utility of a lazy contractor depends on other contractors. If all other contractors are lazy, he will not be caught. So his utility will be this reward minus a lower cost actually. And if there's at least one honest contractor in the group employed by the boss, this will mean a lazy contractor will definitely get caught. Because remember, with hashing, they cannot return the same answer as the honest contractors. So they will be caught, which means they will be fined and they will also pay a cost. But even though that's the case, there's still a problem. There are two equilibria in this game. They can be all lazy. In this case, they get the reward and pay a low cost. Or they can be all honest. In this case, they get a reward, of course, but they have a higher cost. So the utility of all of the contractors being lazy is higher. So that's a better option at this point. So what can we do about it? Let me show you two ways to break this equilibrium. One way is that if we can assume that there are some fraction of the contractors who are honest in the system. So some contractors are honest. Then when employing a group of m contractors, the find to reward ratio can be set using this probability of catching them. This roughly corresponds to the probability that there is an honest contractor in the group. So the probability that you will catch the lazy contractors. In this case, of course, all the contractors will be incentivized to behave honestly. There's an important point here. The boss should not overestimate the number of honest contractors. He can underestimate, but if he overestimates, these incentives won't work. So if we just plot this, let's say the size of the group versus the find to reward ratio for different fraction of honest contractors, we can easily see that even with a group size of 2, this is the least possible group size, you get something like 20-25 for the find to reward ratio, which seems reasonable. And if you have if you have fewer honest users, then you need to use bigger groups to achieve the same find to reward ratio.
I understand. A group of 10 means every computation will be done 10 times over, right?
Yes, exactly.
Which is a fairly hefty penalty.
Yes, which means we want a smaller group size. And of course, this can be combined with random double checking, the first method we talked. So back to our two equilibria case. So I've shown you one way to break it, but what if we cannot assume that there are any honest contractors in the system? So then we can use another way, which is offering an extra reward, bounties. So if you catch a cheater, you will get the reward plus some bounty. So if the bounty is set correctly, which is greater than the reward, assuming there's one job per contractor per round, then again, every rational contractor will behave honestly. So we can again break this equilibrium. Okay, I have told you how to incentivize the rational contractors. We can make them act honestly, but what can we do with malicious contractors? They are irrational. They have some other utility function. For example, Bart here, he just wants to break some vases while cleaning the house. What can we do about him? Like, can we limit the damage? So they want to reduce the accuracy of the system and waste boss's resources. But they still need to keep a non-negative balance to be able to stay in the system. Remember, they won't be employed unless they can pay the fine. And they can be independent or colluding malicious contractors. We'll look at both scenarios. Let's start with independent malicious contractors. So let's define that the amount of time they will correctly compute, the fraction of time actually, the answer as t correct, and the fraction of time they will return bogus answers as t bogus. Remember, they still need to have a non-negative balance to be able to stay in the system. And using that constraint, we want to bound this t bogus. The problem is at this point, with the current fine to reward ratios I have shown you, since they are irrational, they can lie all the time. What can we do about it? So we want to force them act honestly most of the time. So we want to bound this t bogus so that t correct is high. And we don't want to waste boss's resources. The way to do it is to increase the fine to reward ratio. So we introduce a deterrent factor deter, which is a multiplicative factor to increase this fine to reward ratio. So higher deterrent factor means higher fine to reward ratios, and this will cause less maliciousness due to these increased fines. And without wasting any resources, we are not doing more double checking or anything. We are not employing more people. So then, in the paper we show that the t bogus, the amount of time an independent malicious contractor can lie, is bounded with this inequality. And this means the probability of an incorrect result getting accepted is the fraction of malicious users times the probability that they are not caught times this t bogus, the amount of the fraction of time they can lie. Just to give an example, if there are 5% malicious users with a deterrent factor of 5, this will mean at most 1% of accuracy loss, even with a very small probability of catching them. So if you plot this, the deterrent factor versus the fraction of incorrect results with different fractions of malicious users, we see that, for example, it's obvious that we can minimize the accuracy loss by increasing the deterrent factor. And let's just take some sample points. With a deterrent factor of 3, even with 75% malicious users, we get at most 10% accuracy loss. And for 25% malicious users, we get almost no accuracy loss. And these are really high percents for maliciousness. So what about colluding malicious contractors? Again, we have a worst case assumption. They have full collaboration. They know other people employed by the boss. They always collaborate with each other. This is not even realistic. The boss can employ them sequentially so that they don't know the others in the group. But we make this worst case assumption. So under this assumption, when boss employs all colluders, they will return a bogus result. And they will not be caught because the boss won't be checking the result. They will return all the same incorrect result. So the probability of an incorrect result that gets accepted in this case is that the probability that all group members are colluders, which is the fraction of colluders to the number of contractors employed. What about wasting resources? They also want to waste boss's resources. Their strategy for wasting the resources is that t waste of the time, only one of them will return an incorrect result, and all the others will return the correct result. It's enough for one of them just to cheat, to force the boss to double check. This will cause a disagreement in the group, so the boss will waste its resources. But others will collect the reward to compensate for the fine. And the remaining t correct of the time, all of them will return the correct answer. Again, we want to bound this t waste, and we show that using this deterrent factor, we can bound this t waste, and we give the exact bounds. They are They are not nice inequalities, so I am not showing them, but you can find them in our paper. But the take-home idea is that for every wasted resource they can cause the boss, they have to return the correct answer for some of the jobs. Actually, this is, a good fraction of the jobs. So if we plot this again, the deterrent factor was the fraction of wasted work in some sense, fraction of extra checking for different persons of colluding malicious users. Remember, those are colluding, not just independent. Then we can again see that a higher deterrent factor will minimize it. And even with 75% colluding malicious users, with a, let's say, 7 deterrent factor, we get around 10% extra work. And again, I would argue that these are highly malicious, highly unrealistic scenarios. So as future work, there are some problems that we want to address. What about bootstrapping contractors? I said if they don't have enough balance to pay the fine, they won't be employed. But initially, they have no balance. So what can we do? In the Brownie Points project, there are other means to earn these e-coins, so they can get bootstrapped. But what about some other systems? Also, how can the boss find these optimal parameters of the system? We are planning something like an iterated search. So, for example, boss can adjust the parameters if he observes more or less dishonesty than the model predicts. This can be caused by, as I said, due to an overestimate of the number of honest users in the system. So the boss might be adjusting those and observing the system, trying to find the optimal. So in conclusion, we have shown some through analysis of ways for a trusted boss to employ untrusted contractors to do some computation, such that all rational contractors will participate faithfully, and malicious contractors will have very limited effects on the accuracy loss of the system and wasted resources. And our methods are flexible. We have shown ways to set this fine to reward ratio for different scenarios, and we have shown our methods are highly tolerant to this maliciousness with appropriate choices of parameters. And best of all, at Brown University, we are developing such a system. You can visit our webpage for more information, and thank you for your attendance.
One thing I'm curious about is your model doesn't seem to be consistent with the lottery model of incentives that we see in a lot of applications, like distributed.net does this for their key searches. I don't know if SETI at home does it, but they could. It's sort of the needle in a haystack kind of thing. When you've got a huge space and you're looking for a tiny little thing, and instead of finding people who are trying to cheat, all you have to do is say anybody who's actually the one to find the needle shares in a reward, gets a reward for that. And then there's, yes, you could cheat, but you have no chance of getting the reward if you don't do the work. So.
Yeah, I think the most important difference there is we are trying to have a general outsourcing model. The way you describe it depends heavily on the computation itself, because there's one kind of tiny correct answer and all the rest is wrong. But if you think of a general outsourcing scenario, there can be many other options. So I guess, this also applies to their scenario. With probably different fine to reward ratios. I don't know the exact details, but they have probably a more specialized solution. Although SETI at Home projects don't deal with actually cheaters. There are all those problems, and the hashing solution, as I said, was informally kind of introduced, but not formalized before. So.
Yeah, the key searches of distributed.net do have reward. It would seem that for SETI at home, the simple thing to do would be it probably wouldn't be that hard to find somebody who would offer $1 million for somebody who finds alien life.
Yeah, that should be applicable to there too. Yeah.
A lot of people would just be honest because that's the best chance of winning $1 million.
Also, there is a problem of, I guess then another problem is resiliency against these malicious people. So if you have these fines and rewards, since they need to keep this non-negative balance, they can't be too malicious. They can't be malicious too often. But in that case, they can always claim that they found the result, and you have to double check. You cannot just give them the reward. And if there's no fine there, you cannot prevent them from forcing you to act, kind of. Sure.
There's got to be prior art on this. Until the mid-20th century, there were computation bureaus. They would send computation around, I think, just in the mail to people who would sometimes have a desk calculator and sometimes have pen and paper. And, you know, I don't think many of them were malicious, but I'm sure they made mistakes. And one case I can recall, the guy Richardson that invented numerical weather forecasting figured he could hire 40,000 people with desk calculators and have them communicate via light beam and beat the weather in computation speed. And he did think it out.
And they did this?
I'm sorry?
And they really did this?
No, I mean, he didn't have the money to hire 40,000 people. Also, he spent 20 years predicting one day over Germany and found a typhoon that wasn't there. But of course, he was the first. But computation bureaus have been around, I would, not since Adam and Eve, but since sometime 19th century, I would guess, until pretty much computers became possible to get without bribing the Pope, which is about 1950, maybe 1960. So there's got to be prior art. Not that I know what they would do.
That's the problem. I had the same guess. I would expect there would be like more work on this previously, but I don't know. I mean, we couldn't find those. If you know some of them, like it would be great. But
on numerical weather forecasting, he clearly had a very ambitious paper design.
What types of applications do you have in mind at Brown? Is it specific to Brown or Brown students or?
no, actually, the one we are developing at Brown is. So at this point, I have a question to all of you. I have the slides for another talk from the previous year that actually describes the other project we are doing at Brown. Those are interrelated. If you want, I can also go over that, or that's completely your choice. It's the Brownie Points projects I said, using this eCache in the file sharing scenario, the peer-to-peer network scenario. So this project came out of that actually, because we were using this eCache in the peer-to-peer file sharing. There were so many users, tens of millions of users, and there will be so many transactions going on. So the bank will be a bottleneck actually. So we said, okay, how can we outsource this bank's computation to other users? And this project came out of that.
Yeah, that's why I was asking actually. So I definitely want to see the other slides. I don't know about anybody else, but that's what
Sounds good to me.
I think you had told me about that, so it'd be great.
Sure.
You don't need anonymity. Why does it have to be eCache? Because
We want anonymity in this project. In general, for outsourcing, we don't. But there are some other outsourcing scenarios. So this is one of them. The SETI at home, etc. we just said. You can imagine other types of outsourcing. For example, other types of bosses and rewards. One possibility is that, let's say you are a storage server. So you provide some service to other people that they want. For example, storage is a service in that sense. And you want some computation to be done on behalf of you. What you can do is offer storage as a reward and find them by maybe removing people's files or things like those. And this also has its own economy in some sense. So I believe it would be applicable to more scenarios. So this is another project with the same group and also Eric. And the slides are courtesy of Chris Survey. So this is how to make peer-to-peer accountable without losing privacy. This time privacy is important. So what's our problem here? we are looking at a peer-to-peer file sharing scenario like BitTorrent, and it's not fair. It depends on altruism. I will tell more about that. So we will argue that better accountability will provide, first of all, stronger incentives to participate in the system, and also fairness. And the question is that how can we provide this fairness without losing the privacy? It's here. Legal bootlegs of concerts. That's important. So let's say we have Alice as one of our users, and she wants to listen to concert recordings, and she wants to download these legal bootlegs of the concerts using BitTorrent. You know, that's all we do with BitTorrent. We just share legal bootlegs of concerts. Nothing else. Please. Yeah, exactly. Just legal stuff. So then we also have Bob and Carol, who also wants to listen to these concerts and also use BitTorrent to download these concert recordings. So let's say Bob has the whole file, the whole recording, and Carol has some parts of the file. And they are using this BitTorrent network, and Alice contacts them to get this concert recording, but they will not share the data with Alice. Why is this the case? To understand it, we need to understand BitTorrent. So in BitTorrent, there's a central tracker. Tracker keeps a list of peers who has a specific file. So Alice goes to the tracker, asks, I want to download this concert recording. Who has them? Who should I contact? And tracker gives some peers, a list of peers to Alice. Then she contacts those peers directly. So when you contact a peer, there are blocks of data. So each file is split into different blocks. And you tell each other which blocks you already have. And from these, you request a block that you don't have yet. So let's think of BitTorrent working as rounds. In this model, each round, different peers will send Alice data at different rates. For example, in this case, Bob sends 2 blocks at the same time as Carol sends 1 block. So Alice will pick the n fastest neighbors. And let's say n is 1 in this case. So Alice will reciprocate to Bob. She will give 1 block to Bob. But she will choke Carol. So she will not send any data to Carol until the next round begins. So if we go back to our example, remember Bob had the whole file and Carol had some parts of the file, and Alice was trying to download this file from the other people. So, and we said Alice couldn't download anything. Why was this the case? So let's think of Bob. Bob has already downloaded the file, and there's no point for him to just share the file, to upload more, because he won't gain anything. He will just waste his resources. So he leaves the system. His legend remains. But what about Carol? Carol has parts of the file, and she wants to download the rest, those missing blocks. But Alice has no blocks of interest. She cannot offer anything to Carol. So why would Carol give Alice something? Again, Carol chokes Alice, and then she cannot download. So the problem is Alice can only begin participating in this BitTorrent network with some built-in altruism mechanisms. Either Bob needs to just upload the data without expecting anything in return, or Carol should optimistically unchoke Alice and give her data. And the problem is that those ways of altruism is easy to exploit. So BitTorrent was introduced in 2003 by Cohen, and then just 2 years later, that Junan Ahmed found that these incentives in the BitTorrent, these altruism mechanisms, provide free riding. And Baramba et al., this is actually a Microsoft work. They worked on different tit-for-tat mechanisms to just reduce this free riding. And there are 2 famous clients, BitThief and BitTyrant, which try to make use of these altruism, either from seeders or optimistic unchokings, to just free ride in the BitTorrent system. And they demonstrate that this free riding is effective. So we said that the BitTorrent makes free riding easy because of these optimistic unchoking and the altruistic behavior, and so it's vulnerable to such selfish clients. And also it's unfair. The performance of the BitTorrent network relies on a small number of altruistic peers which have high upload bandwidths. And as we just said, after you download a file, there's no incentive to stay in the system because you are not gaining anything. You will just give away free data. So there's some prior work on providing the accountability and like preventing this free riding in BitTorrent. One way of doing it is having private ratio tracking communities. So you cannot download, let's say, more than 2 times you upload, something like that. But the problem is those ratios, your client just tells the server, I downloaded this much, I uploaded that much, and those are easily forgeable. So there's no point, actually. What about reputation systems? They were proposed, and so there are again problems. You need global pseudonyms to be able to resist the Sybil attacks. But in this case, they are not private. If you have local reputation, the problem is it doesn't scale well to a peer-to-peer system of tens of millions of users. So we propose using currency-based accountability. So let's think about currency. Currency is fungible. You earn money, the real-life cash, at Microsoft or MSR, and then you go use that money to pay for something else. And it's secure, it's unforgeable. It's private, it's untraceable, the real-life cash. So we need a digital equivalent of this, which is eCash, first introduced by Chaum in '83. So it provides this fungible credit for future service, and it provides anonymity and unlinkability and unforgeability, everything we want. So what instantiation of the eCash we'll use? It's the endorsed eCash. Actually, Mira's work. This is Kamenich, Lisianskaya, and Meyerovich. So it supports enforceable contracts. What it means? There's a contract between the buyer and the seller, and it can be enforced by a trusted third party. So it also enables efficient, optimistic fair exchange. I'll talk about these, actually. And then it supports efficient withdrawal of multiple coins. So in our system, we will have a bank, and all the peers will have a bank account. So then, when they upload, when they contribute to the system, they will earn eCash. And then when they want to download, when they want to use the services of the system, they need to pay. So how will they do these? We'll show 2 protocols, to buy files and to barter files. And as I said, these protocols will be optimistic, which means there'll be a trusted third party named the arbiter, but he will get involved only if there's a dispute between the parties, and he will use this contract to resolve these disputes. So just to overview the endorsed eCash, there's this bank and Alice and Bob. So Alice goes to the bank, requests, let's say 100 coins, like multiple coins, and then gets them. And then Alice takes one of these coins, encrypts it, and then sends the encrypted coin to Bob. So then what they can do is they can perform a fair exchange of this key to the coin with the concert recording. Then Bob can decrypt this, get the coin, and deposit it to the bank, and bank will not know that it was Alice's coin. This is where the anonymity and unlinkability comes. So I'll talk about how to perform this fair exchange next. This is our buy protocol. So Bob will pick a key K and then encrypt the block he has, and then send it to Alice. At this point, Alice gained no information. Then Alice will, as I just said, encrypt this coin and then put the key in an escrow over the arbiter's public key. So this escrow has a contract associated with it. It says if Bob provides this correct key for this block, the correct key is identified through hashes. Then the arbiter will decrypt this and give the key to the Bob. And this is a verifiable escrow, which means at this point, Bob can verify that this key in the escrow will really decrypt this coin. And after that, Bob can freely send his key and get Alice's key. As I said, both parties are protected. If Bob doesn't send his key here, Alice won't send her key. So it's good. If Bob sends his key but Alice doesn't, then Bob can go to the arbiter and take the key to the coin. So this is an efficient, optimistic fair exchange protocol. Again, optimistic in the sense that the arbiter won't need to even know about it unless one of the parties cheat and they need to resolve. And there's no need to consult the bank. And also, the idea of actually exchanging the key with the key in some sense, so the coin key with the block key, is much more efficient than exchanging the whole block and the whole coin. And this, remember, the Bob sent the ciphertext first and then they exchanged the keys. This actually decouples the data transfer from these accountability issues. And also, it fits the BitTorrent semantics, these optimistic unchoking, etc. So, have we solved the problems? Yes, for the following. We showed a way to prevent this free riding, because you need to keep this non-negative balance. Your balance can't go to zero. And we have shown some incentives to continue seeding. Since the reward is fungible, even when you are finished downloading, you will continue uploading so that you can use this money to later on to buy files. And we moved to a currency economy, which means no longer we need the peers to have a coinciding interest. They can have different interests. They may want to download different files, but they can still interact through the currency. But there are still some issues. As I said, so in this framework, in the endorsed eCash framework, actually for the eCash it's kind of a general result, but users must redeposit the money they earn before they can spend it for something else. So this means bank will be a bottleneck. And this is actually the talk I just gave, like the other one, the Incentivizing Outsourced Computation. So this is a way to outsource this cumbersome job. But also, there are two other ways of doing it. I mean, those are complementary in some sense. We can use multiple coin denominations, like $1, $5, $10 coins. So if you exchange 10 blocks, instead of giving 10 $1 coins, you can just give one $10 coin. And also, I will show you in a second a barter protocol, which means there's no coin exchange. So I just give you a file, you just give me a file back. And so this means there's no need for banks in moment. And it's nice to see that BitTorrent also already does some loose bartering. It's not good enough, but already does some, so we can exploit it. So how can we do that? This is a protocol not in our paper, actually. We improved it later on, so I will show you the improved version directly. So Alice and Bob want to exchange 2 blocks. So at first, Alice, again, takes a coin, encrypts it, escrows it, the key, and sends it to Bob. So this will be kind of a warranty. In case Alice cheats, Bob can use it. Then Bob will send his encrypted block, and Alice will send her encrypted block. And then they will exchange the keys. Again, if Bob doesn't send his key, Alice won't reply with her key, so that's all good. If Alice doesn't send her key, even though Bob sent it, Bob can go to the arbiter, take the escrowed key, and use the eCoin, which means this turns into a buy protocol.
What's this about Bob getting the key and then going to escrow with the same files?
So, I'm not showing the whole protocol here, but it's first of all related to the related to this contract, and also there are different versions of it. We have 2 versions. One uses timeouts and one does not, and I'm showing the one that uses the timeouts because it's more efficient. I mean, the other version has another coin going this way, so it's not too bad, but that's it. I can talk to you afterwards if you want. So the next issue, what about fairness versus performance? So one might argue that introducing currency will make the users greedy. They no longer want to be altruistic. They no longer just want to give away data. Will this hurt the performance? We have a counter argument. So having currency, which means fungibility, will provide better incentive to participate. So at this point, all the BitTorrent clients have a setting where you can limit your upload bandwidth. The problem is you don't get proportional service if you increase your upload bandwidth. There's no real incentive at this point to increase your upload limit, the bandwidth limit. But if you have currency, if it is fungible, then you will just upload so that later on you can download easily. And in terms of the fault tolerance systems point of view, relying on a small number of altruistic users is bad. We are kind of distributing the share of the work to everyone so that it's much better in terms of fault tolerance. What about monetary policy? Where does the eCash come from? How do the new users get this eCash? So we cannot just give out eCash to every new user because this will be susceptible to Sybil attacks. So instead, we are planning to rely on social networks, such as your friend can give you a file or an eCoin to just get you started. Or if you already have a file to share, you can just enter the system with that. But what about regulating the money supply? In this context, the amount of money in the system bounds the number of possible simultaneous transactions. So there's a Cash et al. Paper on script systems. They show that you need to inject money into the system until a point where a money crash occurs. And they show that an entity, a central entity, which has the knowledge about all these money distributions, can perform this, which corresponds to our bank. So our bank knows who has how, I mean, not who has, but like what's the money distribution. So it can be easily adjusted. And the idea is that bank can participate in the system. To inject money into the system, bank can buy files, so give users money. To dismiss money from the system, bank can upload, sell, and then just discard money. Also, there's the issue of fixed versus variable pricing. Will the blocks be fixed priced, which gives more control to bank, or do we want a market economy based on variable pricing, etc., which are interesting challenges, but we leave them as open questions for mostly economics researchers, actually. It's kind of out of our scope. Finally, I would like to mention that the idea of using this eCash in peer-to-peer systems applied to some other peer-to-peer systems too. So the onion routing, again in Mira's endorsed eCash paper, the onion routing says every router on the path needs to decrypt the message and then sends it to the next router. But there's no incentive for them to just keep sending messages. With eCash, if you get paid only after you send the message to the next router, this provides an incentive. For distributed computing, I just talked about it. We can incentivize this outsourced computation using these eCoins as rewards and fines. And we have a work in progress on storage, outsourced storage. So you can think of using these eCoins and contracts and this escrow to kind of providing a warranty to the user in case the server destroys or modifies the data. Similarly, for distributed hash table lookups, again, another distributed like peer-to-peer system, these contracts may specify that you will get paid only if the peer you give to me is like halfway closer to my destination. So in conclusion, we have shown that eCash can provide accountability in such peer-to-peer systems, especially in this scenario, the BitTorrent file sharing, with being fungible and can provide this fairness and stronger incentives to participate. As I just said, maybe increasing your upload limit, etc. And this can all be done while preserving the privacy. Thank you. please.
Talk about storage.
Uh-huh.
The company's storage is gone, the company is gone. Who can pay enough compensation in such cases? I compare with Microsoft.
Yeah, I mean, I guess it depends on the usage scenario. So, first of all, those will be, in some sense, clearly defined. So, when you are making the contract, it says that this much money will be paid in case of a damage. And you are, all, of course, free to accept or reject the contract and so on. But I agree, it may not be applicable to so important scenarios, although it may still be applicable, depending on the service provider and the user.
A couple of questions.
Sure.
Going back to the first half of your presentation,
Mm-hmm.
so supposing you have a peer-to-peer system for content distribution, but then for the arbiter to do the work of that it has to do, you're thinking of outsourcing that. I mean, you're building a system for outsourcing, and what I'm wondering is, first of all, like who will do the outsourcing? Like, will it be pushed back to peers in the same credit system, and then also what's the communication cost for that outsourcing?
Yes, so 2 good questions. To the first one, so as I said, after this project, we realized that bank will be a bottleneck, and we decided to outsource it. The initial idea is that the users in this BitTorrent system, they are using their bandwidth to transfer files, but they have available CPU time. So the computation, the verification of these eCoins can be performed by, again, the users of the BitTorrent file sharing system. So the idea is that they will deposit the coins, and bank will randomly assign different people to check these coins. But in terms of the network cost, at this point we don't have any numbers. I don't know at this point. We realized that the computation, we have numbers for computation, and it will be a bottleneck, but we don't have numbers for the network cost at this point.
But just to get a ballpark idea, would you estimate that, like, say to do one verification, which how many peers do you think you're going to outsource, each verification to?
Hopefully 2.
2?
Depending
okay.
on, of course.
And the size of these, I mean, these are built on public keys or?
So the size of each coin will be around 10 kilobytes.
10 kilobytes.
Yes.
Okay, so, and yeah, by the way, is it going to be like a public key or a symmetric key or any? Or
It will
no?
be public.
Yeah.
It's about 20 exponentiations to verify.
No, I actually meant the size of the eCoin being transmitted.
Yeah, it's about 10
kilobytes,
kilobytes.
right, okay, good.
Per coin.
My other comment was about the peer-to-peer scenario.
Mhm.
So I don't know whether BitTorrent has moved towards this, but I mean, a lot of people talk about and analyze network coding as a mechanism for exchanging. I mean, it wouldn't really change the motivation that you have for having this fair exchange procedure, but I mean, it would certainly change the bottleneck situation for the peers exchanging blocks and things. So they use network coding to kind of change the topology of the spread of the content.
You mean getting peers close to each other to
No,
exchange
it
data, or?
means just all the blocks are randomly, linearly combined and sent to everyone. So you're never waiting for just one particular block. You
I
can
see.
use essentially all information that's given to you at any time.
I see.
It's kind of optimal in terms of like throughput. I mean, you still would want fair exchange for having exchanged your blocks, but.
I mean, I guess you still want fairness and provide incentives, because again, once you download whatever you need, there's no point in giving other people what you have. So you still, probably those works might be complementary. Like, in addition to our work, it might be kind of a more network type of optimization, but you still need those incentives to. Yeah, they might.
Oh, the contract, yes.
So one of them we found is that there's a big temporal problem. So one of the members of our group wants to try to download an audio version of Harry Potter unfortunately, there's an audio version of Harry Potter which came out several years ago, so there's 5 other people interested in it. But very clearly, 5 years ago, there were thousands of people who had downloaded, but those people no longer had any incentive to keep, sharing that. And that's something that corporate coding is not going to really solve, because you
You
want
don't
to
have enough people distributing it.
Yeah.
Well, no, because you don't want to network code every single possible file all as
No.
one giant lump.
No.
Just a quick small thing. I couldn't tell because the details really weren't there, but the fair exchange looked a lot like Macaulay's Peppercoin. Are you using the same sort of thing there?
It's closer to Asacon, Shoup, and Widener.
Okay.
Yeah.
So the overhead, when you exchange a file and you exchange the coin, or
So-
actually the escrowed coin and then the key, the extra amount that you're sending there is not very significant either.
So the idea here is that after this first step, this can be performed as many times as you want, unless one of the parties cheat. So it's kind of only overhead of encrypting and decrypting, which is not a network overhead. So in terms of network overhead, this is negligible actually. Okay, thanks.